Welcome to Worst Case Analysis using Mathematica. In this video, we're going to look at doing a Kirchhoff current law solution. And this is brought to you by Right Paradigm Consulting. My name is Jay Oplinger. I'm the author. So this time I thought we would look at an active low-pass filter. And I've given you the circuit here with the nodes labeled A, B, C, and D. And also the op-amp error model we will use. And from that we will begin to write the nodal equations. And we'll label them IA, IB, IC, and ID. So the first input is VA minus VN over R1. And then VA minus VD times C2S using the Laplace impedance. And then VA minus VB over R2. Now for the B, we're going to use VB minus VA over R2, VB minus 0 times C1S, and then that input goes directly into the op-amp. And so notice that the IOS, the offset current, is flowing into the node, so that's positive, but IB, the bias current, is flowing out of the node, so it's negative. Now let's look at IC. IC is VC minus 0 over R3, then VC minus VD over R4. There we go. And notice that both the currents IB and IOS are leaving the node, so they're both negative. And then we have VC, which is here, and there, VC up through the op-amp to VB, so it's VC minus VOS minus VB divided by Rn. Here's Rn. And then this we consider to be an ideal op-amp. Now the transfer function, we're going to call that EQVY, is the gain of the op-amp, AOL, times VC minus VOS minus VB. And then finally we look at the node VD, and VD is VD minus VC over R4, VD minus VA times C2S, and also we have those two terms, and then VD, which is at the output, minus VY, which is the output of our ideal op-amp, divided by our RO, the output. So now notice what we're going to do is write this equation and then substitute in our value for Vy using this simple equation. That gives us an easy way to put it all together, where each term is pretty simple. Now, the next thing we want to collect all the terms and list them as EQ1, EQ2, etc., etc. So we're going to use the built-in Mathematica function collect and go through all those equations and do that. And here you can see how it does a nice job of collecting all the terms for us. Now we're going to invoke the function that we created in the second video and then create our matrix of this. And now here's all the constant terms, and they equal here are the terms of the transfer function matrix and the voltages. Now we're interested in VD, which, if you remember from the schematic, VD is the output voltage. We want to see what the output voltage is. So that's the fourth element. So we hit solve, and we get Mathematica does the solution and creates our transfer function. Now notice that the transfer function just doesn't have Vn times a bunch of stuff divided by a bunch of stuff. Vn is like mixed in with everything in this case. So that means we're not going to be able to get a pure transfer function. We're going to end up with a transfer function that's a function of the input voltage. So that's a little bit disconcerting, but it's not unusual. So now let's do the sensitivity analysis. The first step, of course, is we need to find a list of all the variables that are in the circuit equations. And then when we make up the variable table, so we can avoid writing a whole bunch of 10 to the third and 10 to the minus sixth operations, we'll just define k as 10 to the third and mu as 10 to the minus sixth. And then we can write them out as we normally would do. So now we're going to use nominal values for the circuit and do the sensitivity analysis. So we do this by creating a table of every variable and its derivative with respect to all the variables, or that particular variable, substitute in the variable table, and then if it's positive, we assume the tolerances are going to go low to high, and if it's negative, they're going to go high to low. So here's that list, that table that we're going to use. Now at this point we have not chosen an op amp, so let's just assume it's an ISL 70444 SEH device, and we'll assume the resistors are 1% tolerance with another 1% to account for end-of-life deviations and temperature operation. Capacitors are assumed to have a total tolerance of minus 19% to 15%, which takes into account the initial tolerance, the temperature variation, and end of life. I wanted to make these different so that you could see that those are easy to handle when you're using them in Mathematica. So if we plot these in, notice R1 here, here's R1 is a positive number, so the tolerances are going to go low to high. R3, on the other hand, is a negative number, so let's find R3, and here the tolerances go high to low. So you just go in and set all those up, and now things like the output resistance, IB, IOS, and VOS you get from the spec sheet for the ISL 70444 SEH. So now we have the real variable table that has both minimum and maximum values in it. So now it actually start doing the easier part, which is just looking at what's the circuit response to this analysis. Now, since it's a function of the input voltage, we're going to plot the circuit response at DC, so S is equal to 0, for V in going from minus 5 volts to 5 volts. So let's take a look at that. And here we end up with a nice graph that shows us what the relationship is, and the two lines are the difference between the minimum and maximum values. Now maybe we're operating mainly around 1.5 kilohertz. Then let's do the same thing for 1.5 kilohertz. And now notice that the transfer function has changed values in terms of where the mins and the maxes are. So this brings to mind, well, what happens as if we would step through a series of frequencies? What would happen to this kind of DC response, in a sense, or a plot for both min and max? Well, what we can do is use Mathematica's animate function and get a whole series of these. So what we're going to do is we're going to create an animation and allow the frequency to vary between 0 and 2.5 kilohertz by 100 kilohertz steps. And then we'll put that in the plot label so we can look at what happens. So here we have an animation that shows us what happens as the frequency changes for the inputs between plus and minus 5 volts. Now I've also jazzed this up a little bit by put shading areas in so that you can see where the circuit could possibly operate is all the shaded areas. And that's one of the things you want to do when you do worst case analysis. Now we can slow this animation down a little bit so we can get a better look at each one of the frequencies as it happens. So this is one little trick you can use to kind of make your report, especially if it's an active report, a little bit nicer for your customer to read. Now let's go to doing a Bode plot. So we're going to assume that the input voltage is 5 volts and look at the frequency response. So again, we're going to take the V0, we're going to substitute in the variable table, and S is I2 pi F. And then we're going to make a Bode plot at Vin equals 5 volts. And here we have that typical Bode plot, and notice the space in here is between the minimum and maximum values, and that's where the circuit could operate, anywhere in between there. Now let's say your input might be 1 volt. So let's change that to 1 volt and make another plot that way. And again, the area between these two lines gives you what possible operating regions there are. Now let's say we want to look at how does the Bode plot change as the input voltage changes. Again, we can use this animate function. We're going to go from a voltage of minus 5 input to plus 5 input every 2 volts. And we're going to create an animation which shows us what the variations are. And we can slow this down. And again, I've shaded the areas in so you can see exactly where the variations are going to be. So hopefully this has shown you some of the power that you can use in Mathematica to do worst case analysis and have lots of options for giving customers a visual display of what the results are from your worst case analysis. Thanks, and have a good day.